Okay, a video on section 2.3, interpretations of the derivative in our class Calculus for Middle School Teachers this summer. I'm Matt Roscoe at the University of Montana. Well, I want to talk to you about two things today, alternate notations and then how we can interpret the derivative. Let's go ahead and talk about alternate notations first. Unfortunately, as in so many languages, there are different ways to say the same thing, and that maxim holds true for calculus certainly. And it turns out that there are two different competing notations for calculus that are used. The two notations bear existence to, or I should say, exist and bear witness to the historical discovery of calculus. So the two notations are on the left and the right-hand side of the equal sign here. So, and we have notations both for the derivative at a point, that is the slope of the function when x is equal to a. We've called that up till this point f prime of a, the left-hand side, and it turns out that notation comes to us through calculus, one of calculus's chief inventors, and that is Sir Isaac Newton. He was the one who first used a notation, not exactly the prime notation. He actually used dots, but one that has been, I guess, changed and arrives to us today is the f prime notation. So slope of the function at the point x equals a, f prime of a. Well, the other way that we write this same idea in mathematics is on the right-hand side of this equal sign, and that is dy dx. That's the fraction we see there. Sometimes we say dy over dx, but usually you hear people say dy dx. And then the vertical bar means evaluated at a. Your book has a really nice explanation of why we might want to call this dy dx. Well, I mean, d stands for delta or change, and so we think of the change in y over the change in x when x is equal to a. So the slope of the function at x equals a, delta y, delta x. So that gets a little bit more simple when we talk about the derivative function. So no longer the derivative evaluated at a certain point, but the general function, the graphs that we've been generating in the previous chapter, or I should say previous section. So we call it just f prime of x if we want to talk about generally the derivative function, and we call it dy dx if we want to talk about it on the right-hand side using the new notation. I should say quickly where that new notation, the stuff that's on the right-hand side of the equal sign, comes from. It turns out that across the English Channel, calculus was being explored and discovered by another famous mathematician in parallel with Sir Isaac Newton, and that was Gottfried Leibniz. And Leibniz preferred the notation on the right-hand side of the equal sign. And it turns out that it's kind of an interesting thing that since both of these mathematicians discovered calculus in at precisely the same time period, but across the English Channel from one another, that they both are, to this date, given some credit in the notation that we use. It is kind of interesting to note too that Sir Isaac Newton was largely driven by applications. He wanted to understand celestial motion, celestial mechanics, if we want to call it that. How we can quantify gravitational changes and how they affect the elliptical orbits of the planets, for example. And so the left-hand side notation is primarily used by the applied sciences. So it's much preferred by the physics community and other applied sciences. Whereas the right-hand side notation, the Leibnizian notation, we sometimes call it, coming to us from Gottfried Leibniz, in Germany, that notation seems to be chiefly preferred among mathematicians, and it turns out Leibniz wasn't driven by any practical application of calculus. He was what we might call today a pure mathematician, investigating mathematics for its own sake, not out of some application-driven end. So kind of interesting historical footnote there, and I invite you to go and investigate the calculus controversy, it's sometimes called, as to who gets historical credit for its discovery. There's also two alternate Leibniz notations, or Leibnizian notations. So sometimes people write it dy dx, and other times people write it d over dx, or d by dx, sometimes we say, of y. So the left-hand side, we often read that as dy over dx or just dy dx. And the right-hand side is often read the derivative with respect to x of y. One of the things that Leibniz's notation does offer us is to think about the derivative as as a functional operator. It's something we do to y. We take its derivative with respect to x. So you can start thinking of differentiation as sort of functionally driven, that there are certain rules and procedures we do when we want to take the derivative of a certain function. So we can think of it as a differential operator sometimes, just like we think about addition as an operation, or taking the square of a number as an operation. We can think of taking a derivative of a function as an operator. So just to sort of make sure we're all on the same page, let's use some alternate notation to investigate the graph of y equals f of x equals x squared. So what would it mean if we were to try to find f prime of 5? What would it mean if we were trying to find d by dx of y? What would it mean if we were trying to find or the derivative with respect to x of y? And number 3, what would it mean if we were trying to find dy dx evaluated at x equals -3? And finally, what would it mean if we were asked to find f prime of x? So let me just write these down. So let's see, number 1, f prime of 5. Number 2, d by dx of y. Number 3, what are we looking for there? d by dy dx evaluated at x equals -3. And let's see, number 4, we're trying to find f prime of x. Okay, I've got those written down. Let's go ahead and get into some technology. So I'll switch over into Desmos in this first example and show you how you can use technology to answer these types of questions. So the first thing I would ask is, well, what are we trying to find? We're trying to find f prime of 5, but f of x itself is equal to x squared, right? So I'm going to put x squared in there. There's the graph of x squared, just what we expect it to be, some sort of parabola, and we're interested in f prime of 5. So, we really want to know, well, let's put a point on this graph. So I'm going to put a point in by typing in a comma f of a. And it'll ask me right away if I want to add a slider. I will add a slider. It adds one from -10 to 10. So a comma f of a always is a way to, if it's not an x or a y, it immediately thinks, oh, you want me to give you a slider. So it'll prompt you for a slider. So in effect, what this is doing is putting this value of a into as a point, and then putting a through the function to find out what f of a is. So we're kind of interested in what's going on at 5. So let's put it over here at 5. Of course, it's off the screen, so we'll have to change the graph window. So the y-axis is where we need to add some height. Well, 5 squared is 25, so let's go, well, let's go at least up to 50 just to see what this thing looks like. Okay, well, there we see it now. It's right at 5. And what we're being asked to find or evaluate is the graph of the function, or should say the slope of the function right there. So somehow we'd like to know what the slope of the function is right there. Well, when I look at that slope of that function, I think to myself, well, I could do it a couple different ways. If I had it written out, I would just draw a line, but I can see that the slope of the function here is very close to being a line. And if I zoom in on it a bit, it's kind of nice in Desmos because you get to make your scale is maintained here down on the bottom, even though the x-axis has gone away. So if I just look at, for example, this little triangle right in here, I can see that it has a rise of 5 units and it has a run. Let's see, if this is 4 and that's 5, then we've got 4 units in between there, squares in between there. Each square must be a quarter. So each one of these squares is a quarter in the horizontal sense. So a quarter, a half, it looks like it's gone over a half, and it's gone up 5 units. So if it's going over a half and up 5 units, roughly, that's the slope of the line in there, then we might estimate the slope to be 5 divided by a half, so somewhere in the neighborhood of 10, because there are 10 halves in 5. So a rise over run of about 10 units. So I guess the way I would write that down is I go to my page here, and I'd say f prime of x is equal to, and I'll write it in words, this slope of f of x at x equals 5, and that's equal to about a positive 10 is what we think. Now, much different questions being asked next. What's the derivative with respect to x of y? So what we're really after here is the general derivative. What is either the graph of that, but since we're being asked to provide it here, we're going to try to find it, how it could be represented algebraically. Of course, we've been asked to do graphs up until this point. And this really highlights the nice thing about Desmos is that it uses Leibniz's notation for derivatives. So if you divide d by dx of any, go up here to the top, of any function, so f of x, then it'll just basically show you what that derivative function is. And what's nice here is that you can see that we were pretty good in our guess. If the purple function is the derivative of the red function, then at 5, the purple function should be valued at 10, just what we just found, and it turns out it is valued at 10 there. And the big question is well, what is this function? And I've given you one that you should be able to recognize right away. It's a line, and so it's a line that goes through 0, it looks like. So it's of form y equals mx plus b, but b is 0. So all we need to do is figure out what the slope of this line is, and it's fairly quickly, easily found, because we can use this point that we just found, which was the derivative at 5, to find out that it has a rise of 5, but a rise of 10 and a run of 5. So it's 10 over 5. So 10 divided by 5 is 2. So the graph of this function better be 2x. And of course, we could check this by just graphing y equals 2x. And there it is. The orange function seems to be on top of the blue function. I'll click it on and off just to make sure you're aware of what I'm doing. So using technology, we were able to find that the derivative of the function x squared is indeed 2x. So let's go ahead and write that down. So it appears that the derivative of this is, so this is what we're being asked here is for the derivative function of, so that appears to be 2x, which seems to make sense because 2 times 5 is 10, and that's what the derivative valued at 5 should be. So now let's go down to the next one we've been asked for. We know that dy dx, the derivative of y with respect to x, evaluated at x equals -3 is what we're being asked for. Another way to write this using, if you prefer, Newton's notation would be f prime of -3. So we're literally trying to find the slope of the function at x equals -3. Well, we have this derivative function. We could just plug it in there, and then we'll go to the technology to verify. So if I put a -3 in the derivative function, it should tell me what the slope is at -3. So 2 times -3 would be -6. Let's go to the technology and see if that seems to make sense. So I'll move my point back here to -3-ish. And does it look like that could have a slope of -6? Let's see. So how could I do this quickly? It's roughly equal to the slope of it could be roughly estimated by looking at the slope of the line. Let's put it on 3 though. See if we can get it right on 3. There we go. So it looks like if I went, let's see, so if I went down, where am I at right now? -3 squared should be at 9. Yeah, that's right, 8, 8.5, 9. So there it is. So if I went down 1 to 8, I would go over 1 and a half of these little squares, but each little square, it looks like, is a tenth. Let's see, so -3, 1/10, so 15 100ths roughly. So 1 over 15/100ths is what we get when we do the rise over the run. But the rise, of course, is negative, so it'd be negative 1 over 15/100ths. When I hit that on my calculator, what do I get? Let's see. Let's try negative, oops. Sorry, negative 1 divided by 0.15. What do I get? I get roughly negative 6 3/4, so maybe I'm a little bit off in my measurement, but it seems to be in the ballpark for a slope of negative 6, and surely the derivative function seems to be reporting that at 3 the slope is indeed negative 6. So I'm going to use negative 6 as my answer there. And then the last thing is, well, what is f prime of x? And we know that f prime of x is the same thing as the derivative of f at x. It's the derivative function again, so it's the same thing as what's being asked for in number 2. So what I want to make sure you're very aware of is that 2 and 3 we're asking for the same thing, and 1 and 3 we're asking the same type of question, but at different points, at different values of x for the function. So this one was asking for the slope when x is 5. This one was asking for the slope when x was equal to negative 3. Okay, well, let's move on. I hope that gave you some ideas about the different uses of notation. You'll have to get used to both of these notations if you study calculus for long. So let's talk about interpreting the derivative. So let's suppose that the cost in dollars of building a house that is a square feet in area is given by some function, C equals f of a. Interpret each of the following statements and provide the units of each. So let's think a little bit about what we have here. The cost in dollars building a house, so how much it costs to build a house. It's a function of how many square feet. You know, how big the house is should drive up cost. I would assume that this is an increasing function. I guess we'll find out. And then we'll interpret each of the following statements and provide the units. Okay. So let's see here. So the first one says f of 1,700 equals $165,000. So what do we mean by that? So let's give myself some space here and bring up a little bit of a work spot here. So what does it mean? So f of 1,700 equals $165,000, right? Sorry, I just gave it away. So let's see, f of a is equal to c is the template we should be using. So that means a here is equal to 1,700, c is equal to 165,000, and what we know is that a is an area, so that's in square feet, and c is a cost, so that's in dollars. So if we were to interpret this, we would say that this particular function predicts a cost of $165,000 is predicted by a house that is what? 1,700 square feet in size. So this was simply an input-output. If we know the square footage, then we can predict the house's cost to build. All right, so that's number 1. Let's go ahead and go to number 2. I'll try to do it on the same, since it's linked. F prime of 1,700 is going to be equal to 57. So let's think about this. So what is f prime equal to? That's the rate of change, right, of the function with respect to the x. So in this case, what that means is, so this is, how do we kind of think about this? This is how the function is changing its slope, right, at a certain value of a. So this thing over here is equal to a slope, right? So let's kind of draw a quick little picture here of what we think is going on. I'm going to do it up on this upper right hand. We have some graph, although we've not been given the graph, that says that the function, the cost, is a function of a. So that means the function, which is usually plotted on the y, so the function itself is the cost, is some function of area. Okay, so if we were to have some function drawn in here, then its derivative, c is equal to f of a, right? Where a is along the x-axis. That some function, let's say, I don't know, let's say it looks like that, has some derivative, right? Let's say it's some value 1700. Right here, we know that it's 1700, we're at 165K. I'll do these in black. So we know that that's the value of the function, but now we're being told that the derivative of the function at 1700 is 57. So literally what we're being told is some statement about that line, and its slope is 57. Now if you think about it, the derivative, this number 57, it has to be a slope, right? So it has to be a rise over run unitized number. So in the sense of rise over run, the rise is in cost or terms of dollars, and the run is in square foot, so in terms of square feet. We know that 1700 is actually a square footage, right? Because we're told that the function is a function of a, and a is the area. So what do we got going on here? How do we interpret it? I guess what we would say is that at $1,700, the change per unit square foot is about $57, right, per square foot. So this is the idea here. So for a home or house that costs, that is 1,700 square feet, the price per square foot changes at a rate of $57 per square foot. Okay, so in other words, if you wanted to build a house that was, say, 1701 square feet, 1701 square feet, well, you're going to have to add $57 to your targeted price. And in the neighborhood of 1700, we could use that kind of reasoning. If we wanted to add 10 more square feet, well, we'd have to add say, $570 to our sale price or home value. So in that neighborhood around that point, we could kind of use that proportional reasoning. The reason we can do that is because we kind of hope, I guess it wouldn't be true if there was radical curvature in that neighborhood, but if things are roughly linear around that point, which they often are when there isn't a radical change in slope, then you can use that slope to make predictions around that point. Okay, so I hope that makes sense. Let's go on to number 3 now. I'll erase this. So number 3, we're asked, well, what does f prime of 2,500 equals 45 mean? So similar to the last one, what that means is that for a 2,500 square foot house, let's see, the cost per square foot, what increases at a rate of $45 per square foot. So this is kind of interesting, right? For a larger home, the price per square foot is a little bit less. And if you think about that, I really think that's true, right? You know, the cost for a home probably does get the rate per square foot probably does go down the larger the home you make, and the reason for that is you don't have to add some of the big ticket items. You have to have in every home, so things like plumbing, heating, and electrification. But simply adding more square footage means, well, you have to do a little more plumbing and heating and electrification, but most of it's just in terms of framing, wood and roof and some windows, which perhaps are going to be spread out over that extra square footage at less a rate of change. So I do think that the picture I drew in the first one seems to be what is being indicated here. The slope is actually less steep the farther out we have, so something like this is definitely going on. If we take these 2 points, we know that at 1700 and at, let's see, 2500, we had some sort of slope that was steeper here, and I would assume the 2500 house is going to cost more, but the slope is going to be a little bit less steep. So something like that. I don't know if that's really what's going on, but let's say maybe I should do this a little bit better here. Let's say it looks like that. So the idea here of slopes would be that at this point and at this point, we'd have a little steeper slope here than we would have there. Okay, let's move on and talk a little bit about number 4, and we'll end there with this example. It says the derivative of cost with respect to area evaluated when area is 1,500 square feet is 63. So let's see, derivative cost with respect to area when area is 1,500 feet is 63. So again, for a 1,500 square foot house, the cost per square foot increases at a rate of $63 per square foot. So again, this idea of a smaller home, actually price per square foot is going to be a little bit higher, I think, again, because of the cost of infrastructure, which is spread across a smaller square footage. Okay, hope that makes some sense on that particular idea, interpreting derivative. You can see that that derivatives, the answers to questions 2, 3, and 4 all had to do with things that were rates. Of course, since a derivative is analogous to a slope, and a slope is a ratio of rise to run, then we should often expect that derivatives will be interpreted in terms of rates of change. And let's do one more, and this one, let's try to do this with the calculator, but I'll go ahead and minimize this for now. So it says if t is the number of years since the start of the year 2000, the population P of China in billions can be approximated by this function. Use technology to estimate each of the following, giving units, and explain what these numbers tell you about the population of China. Okay, so we're going to use the calculator here. I want to make sure that you are aware that your calculator can do derivatives as well. So I'm going to pull up my calculator emulator. So it'll be off to the left here, and I'll put my my slide off to, right and left, slide off to the left, calculator off to the right. So I'll go ahead and clear this out. I think the first thing we should do is get a graph of this. So let's go ahead and delete these two things, and I'll put in this thing 1.267. So if you have a graphing calculator, I'm using a TI family calculator. This is kind of the new TI-84 CE, but any TI-83 or 84 keystrokes will be very similar to what I'm doing here. 1.007, and then raise that to the x power, and there is our function. I'm going to just hit a zoom standard, so that's a zoom 6 to get us started. You can see the function comes in, okay, well, pretty low there. It looks like all the change is happening between 1 and 2, which I guess makes sense. This is an exponential function with a base value of 1.2 and, excuse me, a y-intercept of 1.2 and then a growth rate which looks to be very small, 1.007 compounding every t years. So let's think about windows. It doesn't really make sense to give negatives here because we're starting in 2000 and moving forward. We want to know about 16 and 40. So let's go ahead and change our window, make the x minimum 0, make the, let's see, the x maximum, if we want to go to 40, let's make it 50. So the x scale, then, I don't know, we might as well do tens, huh? And let's let the y minimum be, well, if all the action seems to be between 1 and 2, let's start it at 0 and run it to 2. And let's let the scale be tenths there. And I'm going to leave the resolution and trace step the same. Go back to my graph now. Okay, so now we're seeing it. It looks very linear, although we do know this is an exponential function. If I trace it, and then just simply type in the numbers I'm interested in evaluating, 16, enter in trace mode will give me the value of the function 1.416603. So I'm just going to talk through this one rather than write it out. So let's talk about what f of 16 means. Well, this is f of 16. It's the function evaluated at 16, and what we get is 1.416603, and that's the population P of China in billions. 16 years after 2000. So that's what we'd expect at the start of this year, start of 2016, that this model predicts as China's population, 1.416603 billions of people. So that's what f of 16 means. Now, what would f prime of 16 tell us? Well, that would tell us how quickly the population, which is on the y-axis, is changing with respect to time, which is on the x-axis. So I'll go ahead and show you how you can get a derivative from your calculator. If you go to second and trace, that's the calc menu. When you're in a graph, you'll get this menu. You can get the value, the 0, the minimum, maximum, the intersect, or this number 6, which is dy dx. And there it is. When you hit dy dx, when you're on a point, it's very close to this, let's say 16. I'm going to dy dx, there it is. So what is that telling us? It's telling us the change in population in billions per unit time, which unit time here is years when x is equal to 16. So in a sense, what we're getting is 0.009 billions. So I think the way we would interpret this would be it's roughly 9.8 million people per year is how fast it's growing in 2016, or that's what the model predicts instantaneously around that start of 2016. Okay, let's take a look at what it's doing, let's say in quite a time later in 2040. So to do that, I guess the first thing I would do is I'd just put it in trace mode and I'd type in 40 and see what's going on there. So if I do 40, what I'm seeing is that the population is predicted to be 1.674 billion people, so quite a bit more than what we had back in 2016, but not incredibly much more. Well, I guess it is quite a bit more. We think in terms of the scale here, we're talking billions. And let's see what the growth rate is. Here we're asked to find dp dt, or the derivative of p with respect to t evaluated at t equals 40. So how fast is the population changing with respect to time when time is 40 years after 2000? So we're talking about the year 2040. Let's see what's going on there. So we'll go ahead and hit second trace, which gives us the calc menu, and I want to do the 6th item, so I'll just type 6 in there. And you do have to type in 40, enter, and it tells you what dy dx is at 40, and you can see that the rate of change has actually grown quite a bit. We were talking in the last question that f prime of 16 was somewhere in the neighborhood of 9 million people per year. Now we're talking about 0.11 billions. So if we move that decimal point 3 places to the right, we talk about millions. So we're talking about 11.6 million people per year is how fast we're expected to be growing should this model continue to hold true through 2040. So definitely an increase in the rate of change in the future. And that's the exponential function working for you. We know that this thing is bending upward, although very slightly because the base on the exponential is just slightly greater than 1. Okay, I hope that gives you a sense of how to use your calculator to find some of these things. I guess the last thing I want to say is that the units of the derivative of a function are the units of the dependent variable divided by the units of the independent variable. So in other words, if we have something of the form dA dB, or the derivative of A with respect to B, then that thing has, whatever it is valued, it has units that are a ratio of units of A to units of B. In other words, it's literally ratio of rise over run of the graph of A as a function of B. Okay, that's all I wanted to show you in this particular chapter. Good luck on your homework, and please let me know if you have questions.